Hi class, today we're going to be discussing mass calculations for chemical reactions. So basically we're going to be putting everything together that we've learned. You've learned it in sections and we've expanded on each section, and now we're going to learn the final part and we're going to put it all together. So here is a mixture of acetylene and oxygen. Undergoes combustion during welding of metals. We can calculate the mass of acetylene used to weld a specific mass of a metal. So after this section, given the mass in grams of a substance in a reaction, we can calculate the mass in grams of another substance in the reaction. And that's what we're going to learn today. So this is kind of confusing how they set it up. So I made a fake reaction, which really doesn't exist because we only have one reactant and one product. And I didn't want to add other reactants or other products because then it would make this more complicated to understand. So I made a fake reaction that does not exist. But in order for me to explain this, that might make sense with a little, I'm a visual learner, so this helps me. So we have a reactant A and a product B. So I'm going to read this and then I'm going to explain exactly what this means. Given a balanced equation, so let's pretend this is balanced, convert the mass of substance A to substance B by first converting the mass of substance A to moles using the molar mass. Second, converting the moles of substance A to moles of substance B using the mole-mole ratio of B to A in the balanced equation. And third, converting moles of B to grams using molar mass of B. So that might make sense, it may not. So I'm going to go over this now, pointing out some things. So let's say we have a certain amount in mass of A. So that's where we're starting out here. We need to get to grams of B. And these are stepping stones. We have to do certain things in order to do that. And one of those is using conversion factors and molar mass so that we can cancel out the units we don't want. So the first thing we're going to do is take grams of A and take the molar mass of A and set it up to moles of A. That will cancel out the grams and leave the moles. Molar mass is grams over moles. So the molar mass, the mass part, grams would be at the bottom of if you think of a fraction, and moles of A would be on top. So the grams would cancel out. Now we have moles of A, but we need to do a mole to mole factor. So this is where we'd have A over B or B over A, and we would set that up. We would have A on the bottom because A would cancel out the moles, leaving us moles of B. Now we would use molar mass again, which is grams over mole, but this time we would use grams on top because we want this in grams, so the moles of B would cancel out. If this doesn't make sense, it will, because we're going to do an example. So here is an example for us. It says, suppose we want to determine the mass of grams. So mass is always grams. If you hear the term mass, it may not always say grams, but mass means grams, always. Suppose we want to determine the mass of ammonia that can be produced from 32 grams of nitrogen in the following equation. So we are given the equation, we're given 32 grams of nitrogen, and it wants to know the mass of ammonia. So we're going from A to B. So here we have 32 grams of nitrogen, that's to start off with. We need grams of ammonia, and remember, these G's mean gas. So it's ammonia gas, nitrogen gas, hydrogen gas produces ammonia gas. And we need to do a mole to mole factor, and we need the molar masses using this equation. So one of the things that I do, and I have always done even as a student, and I still do now, is I write out the problem. So if there's a balanced equation, I write everything that I know about that substance underneath it. So I can see what I have to work with, and I can see what I'm missing. So in this case, I put 32 grams under nitrogen because that's what was given to me. I leave this one blank because there's nothing that's talking about this one in this reaction. And we want to know the mass. So I put the units grams. This does not mean gas. It means grams with a question mark. So I have to get from A to B. And the way that I'm going to do that is taking the grams of nitrogen, which is 32 grams, using the molar mass of nitrogen, the moles of nitrogen, the mole to mole factor, and then the moles of ammonia, the molar mass of ammonia, and the grams of ammonia. So we have several steps that are going to go on here. So next step, use the mole to mole factors. Write out the molar masses and write them in a conversion factor, so a ratio, so you'll know which ones you need to use. So 1 mole of nitrogen is 28.02 grams of nitrogen. Here we have 1 mole ammonia is 17.04 grams of ammonia. Now I set up here on this one the molar ratio. So 1 mole of nitrogen equals 28.02 grams of nitrogen, and vice versa. And the same thing goes with this one. And now on the bottom one, we have 1 mole of nitrogen equals 2 moles of ammonia. And now we can use that as a conversion factor as well. So we have everything that we need to do this problem. We just have to set it up. So here we take the 32 grams of nitrogen, and nitrogen is the first unit that we want to cancel out. Okay, so if we look here, we have taken all the conversion factors that we need. We set up the 32 grams, and I'll cover the exact sig figs after this because you may be wondering about this. 32 grams of nitrogen, and then we use all the conversion factors we need. So we want to get rid of nitrogen. That cancels out the grams. It leaves us in moles of nitrogen. Now we need to get from moles to ammonia. So this is the conversion factor that goes between the actual balanced equation. So moles of nitrogen on the bottom because we want to cancel these out. And then 2 moles of ammonia is on top. So now we will use the conversion factor for and the molar mass for ammonia, which is here. So this is a molar mass, this is a molar mass. Molar mass for nitrogen, molar mass for ammonia, and that cancels out the moles of ammonia. And now everything gets multiplied. So if you were doing this, I tend to do this in one shot. Some people break this up into steps. The more you break it up, the more chance you have of making a mistake, rounding, doing things that you shouldn't be doing if you just leave it whole. So what I do normally is, this is technically 32 over 1. So I multiply everything on top, and then I divide by everything on the bottom. And you can have your own way of doing it. It doesn't matter. But I end up with this problem, it's 39. So let's look over what is exact and what is not. We start out here with 2 sig figs. Here is a molar mass. 1, when everything's set to 1, that's always exact. So this is 1 mole of nitrogen, that's considered exact. This is 4 sig figs for the molecular mass. Why the molar mass? Why is that? Because some people can shorten this to 28 grams. Some people can make this longer, because if you look at the periodic table, some of these have 4 digits going out after the decimal point. So this varies, and it's a weighted number. It's a weighed number, so it can vary depending on how many sig figs you use. This example is using 4 sig figs, so we're going to use 4 sig figs. Again, this one here is exact. Whatever you're using the coefficients in an actual balanced equation, those are exact. You don't have to worry about them. And now same thing for the molar mass here. 1 mole is always exact, but the molar mass of that substance, this can be 17.0456932. Somebody in class may want to use that. Somebody might just use 17. And that's why you have to follow how many sig figs for the rules, because some people's numbers might be off a little bit. So if everybody's consistent, you should all end up with the same numbers. So 2 sig figs here, this dominates because 4 sig figs is more, 4 sig figs is more. So this number being 39 grams for ammonia is 2 sig figs, because this number is the smallest value of sig figs. So my answer will be in 2 sig figs. Let's do another one. How many grams of oxygen are needed to produce 45.8 grams of iron 3 oxide in the following reaction? So we really don't need to worry about this here, because we can refer back to it if we need to, but we still need to find the answer. So I really wouldn't even worry about looking at this. I would just focus on doing the problem. So here we have 45 grams of iron 3 oxide as the product, but we want to know how many grams of oxygen it took to produce this. So what do we have? We are given 45.8 grams of iron 3 oxide. We need the grams of oxygen. We're going to do the same thing using mole to mole factor and molar masses using the equation. So again, if you follow these steps here, this is going to tell us, and these blues are the stepping stones to get us to the final product. So here we use same thing. We have 1 mole, which gives us our molar mass of iron. And then we have our which we set up here. And then we have 3 moles to 2 moles. So this is our mole to mole ratio. This is 3 to 2, 2 to 3, however you look at it. That one's set up. And then our final one is 1 mole of oxygen equals 32 grams. And then we set up this coefficients, these conversion factors. And now we're going to put it all together. So we start with our 45.8 grams. That's the only mass that's here. And now we're going to we need to get rid of iron 3 oxide. So we're going to use that conversion factor for that, the molar mass of that. And this is the total, 159.70 is the molar mass of iron 3 oxide. So this is for 1 mole. And now we're going to use the conversion factor that's from the balanced equation, the 2 to 3. So that will end up canceling. So the grams cancel, leaving us 1 mole of iron 3 oxide. Now we need to cancel iron 3 oxide. We need to get to moles of oxygen. This is our stepping stone. So we cancel this out. That leaves us a 3 moles of oxygen. And now we're going to use the molar mass of oxygen. And that will get us our 3 sig figs of 13.8. Now, one thing I want to point out, that here it's listed as O2. So this is 32, not 16. You have to account for both atoms of oxygen. So this is 32. Now let's look at the 3 sig figs. 3 sig figs, exact. We don't look at the 1. 5 sig figs. Here we have exact, exact. 4 sig figs, and exact. So we have 3 sig figs here. That's the smallest value. So the answer is going to be in 3 sig figs, and the answer is B. So if we go back, we can look and we see B is the one that we needed for this problem. And hopefully this now makes sense of putting everything together to allow you to understand how to get from point A or substance A to substance B. Thank you.